Alright, so multi-electron system part 2. Alright. So now you learn how to actually write the configuration, electronic configurations for these atoms. You should probably practice by yourself going from the atomic number 19 to atomic number 36. Or maybe that's starting out from 1 to 36. That would be an interesting one. And you can always get the answer check in here. This has actually an electronic configuration at the tail end of it, so you can double check your answers. So let me just try to explain why the periodic table is useful, and then its relation to the electronic configurations, that's ground state electronic configurations. And then we're going to talk about the core electron and valence electrons. So let me just start out with the core electron and the valence electrons. So carbon, for example, let me just try to start out with carbon atom. So the carbon electronic configurations, carbon, right? 1s square, 2s square, 2p2, right? Because carbon have 6 electrons, right? Now, this one right here, n equal 1. And these guys, these 4 electrons, is n equal 2. So the outermost electrons, one with the largest number of n, these guys are valence electrons. Valence electrons. And these are core electrons. So you have 2 core electrons for the carbon and then 4 valence electrons for the carbon atoms. Let me just do one more example. So let's do the p atoms. So for the p atoms, so the p atoms, p atom, phosphorus, I think. So 1s p atom is, what is how many electrons are there? It's 15 electrons. So this has a 15, right? So 1s square, 2s square, 2p6, so that's 10, right? And then 3s square, 3p3, right? Now the largest number of n is n equals 3, these guys, right? So p atom right here actually have 5 valence electrons. And then rest of the stuff, all of these guys are core electrons. The reason why it's called a core is because 1s is the smallest in size, and then 2s is the next smallest one, and 3s, 3p is way out, right? So core electron is something close to the middle. So these 10 electrons orbit around the nucleus very tightly, and then 5 electrons, the valence electrons, stays in outer orbit more or less. Although that in technically speaking, you can't pinpoint the position, so it doesn't really have this orbit shape, but it's sort of like electron clouds tend to stay outward compared to the core electrons. So now I hope you got this idea of the core electron and valence electrons. So let's dive into this periodic table. Now notice that periodic table have a two column right here, and then 6 column right here, 6 column, right? And then one in the middle, like somewhere around here, you have 10 columns right here, right? So starting from here to here, let me just try to starting from here to here, right? There is a 10 columns here. So 2 and 6 and 10. Does it sound somewhat familiar? So let's just count let's see the correlations here. S orbital have one box, right? And then it can accommodate 2 electrons. And that 2 corresponds to right here. That's why it's called S block. And p orbital actually have 3 boxes, right? And then it can accommodate 6 electrons. So that's why you have these things are called p block here. Now right around here you have 10 electrons, right? The 10 columns. And the reason why it's 10 columns is because you have this D block that can accommodate 10 electrons. And then F block right here, you have 7 boxes. 1, 2, 3, 4, 5, 6, 7. Right? Let me just write it down. So, and then all of these guys, I'm just too lazy to actually write out it's 14 electrons, right? So the 14 columns right here. So that's F block. Alright, so we have actually identified this SPDF block. Eliminate that one. Alright. So let's see that the correlations between the off-ball principle and periodic table here. So off-ball principle start out with 1s, oops. It's 1s, 2s, 2p, 3s, 3p, 4s, right? 1s, 2s, 2p, 3s, 3p, 4s, and so on and so forth, 3d, right? So the important things to remember is that p start from 2, right? And then d orbital starts from 3, right? So given that, and then that s starts from 1, s start from 1. Right? 1s, for example, starts from 1, and then that 2p really starts from 2. 2p, 3p, 4p, 5p, and so on and so forth. It starts from 2, right? And then d orbital starts from 3d, 4d, 5d. There is no 2d or there is no 1d, right? Because of that quantum number limitations, right? So these are all related to that quantum number L, right? And L has to be 1 less than the n value, right? So at least. So that said, so let's actually read from the side way. I'm following these numbers here, like 1 and 2 and 3 and 4 and so on and so forth. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, coming back, and then this one is a 5d, and then 6p. So what I'm doing right now is that going in a side way in the periodic table is equivalent to this off-bow principle. So whichever the one that you're comfortable with, it's fine. It's basically it's gonna give you the same stuff. It gives you the ground state electronic configurations. Now, you may be wondering why I'm actually switching from here to somewhere around here to here, right? There is I all of a sudden went this way, right? And notice that there is a gap here, right here. And this F block is actually sort of like coming out. So you just cut out these things and then paste it right in between these things. That's pretty much what's happening here. So CS, BA, LA, and then all the way to YB, and then next up is going to be LU, and so on and so forth. If you notice that 55, 56, 57, 58, blah 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 blah, 70, 71, 72, and so on and so forth, right? So this F block right here is sort of like coming out of this periodic table, in a 3D fashions. So that's pretty much what's going on. But I hope that you did actually realize that this off-bow principle and the periodic table is pretty much the same thing. Alright, so that's that. Now, the main reason that periodic table is useful is that any of those atoms that's in the same columns, for example, like N and P and S and SB and BL or the BI. I can't really see what's this. It's a BI, yeah, BI. All of these things, they react the same way. And if you take a look at this electronic configuration, they should be fairly similar to one another, right? And that's just the start of this periodic table. They actually try to react each one of these atom type, and then classify as these actually react in a similar way. So let's just put everything in the same column. That's the starting point of the periodic table. So all of these guys, like what's in the vertical columns, they actually behave exactly the same way. So if you recall that I was actually talking about these guys right here, these guys react exactly the same way. And if the helium is stable, then neon is stable, argon is stable. Stable means that it's not reactive. Krypton is stable, xenon is stable, and so on and so forth. So yeah, they're called actually noble gas, and noble gas is stable, really. And I still haven't explained that one yet, but not at this moment. I'm gonna explain it a little bit more. I have to explain some other stuff to actually get to that one. So let me just go back to this one. So in order to understand a little bit more about this periodic table and then the property of all those atoms, you will need to probably understand what the Z effective is, and that Z effective is the parameter which can be used to explain the size of the atoms or ionization energy of the atoms or the electron affinities and so on and so forth. So the Z effective is fairly useful tool I'm talking about right here. So let me just try to explain that portion right there. And that's pretty much the main part of this particular part of this video right here. Now, I don't know where you actually learn these things, maybe in the middle school or the high school, that two charges have interactions. If it's positive and negative, they attract, and then negative and negative repel each other, or the positive and positive repel each other, right? Proton is always positive, right? And the electron is always negative. So proton and electrons have attractive interactions. And then electron and electrons, they have repulsive interactions. Okay? That's what you need to memorize. And then, or maybe that need to understand. And then also, if I actually have a 2 positive charge right here, if I have 2 plus charge here and then 1 negative charge here, then that's one case. And then another case is 4 positive charge and then 1 negative charge. The attraction between these two charged particles, this is much stronger than this guy. As the magnitude of the charge increase, the interaction gets more intense. So these guys right here, they attract more than this system right here. The more charge they are, they attract more, become repulsive. And distance is also important too. If the distance gets shorter and shorter, then interaction becomes more intense. And then if the distance is larger, then interaction becomes less intense. So for example, like I don't know if you have ever played with the magnet S and N, right? So there is a south pole and north pole, right? When you actually try to, let me just try to erase some around here. If you have 2 separate magnets like this, and then on this, the interaction is very weak here because of the large distance, right? But if you actually put these things very close, then what's going to happen here? The interaction gets really strong, right? So if you actually played with a really strong magnet, like a neodymium magnet, and you put the fingers in between, that your finger is actually in big trouble, because those two magnets can be a very strong magnet, and then might actually crush your fingers and so on and so forth. So as the magnet gets closer together, the interaction gets more intense, right? The same thing goes with the charge and charge interactions. If the charged particle gets closer together, then that interaction gets really, really strong. It's pretty much all I wanted to say about the charge-charge interactions. So now, instead of actually dive right into this quantum mechanics, I want to actually talk about this sort of like a classic way of actually thinking about this problem. So let's just bear with me for now. So you have this 4 plus charge in the middle, and then these 4 negative charges are moving around in this on this orbit right here. So it's sort of like they're moving around all over the place, right? Now, all of these guys, they actually get attracted to the central charge just because that the distance is closer, right? And then they actually have this 4 plus charge in the middle, right? So the attraction here is much bigger than the repulsive interactions between the electron and negative charge and negative charge here, right? So all of these guys get attracted to this one. So if you actually try to leave this system, what's going to happen is that they are going to probably stay close to the very small circular orbit. Now, in the different scenarios, if I actually have a two negative charge close to the 4 plus charge, and then another two negative charge like outside. So what do you think this guy actually see right here? If the distance is too far away, then the net charge in here, you have 4 plus 2 minus, right? So which is gonna be 2. Net charge of 2, right? So this system right here is same as this guy right here is watching 2 plus in the middle of the orbit. Same goes with this one. This guy see 2 plus charge in the middle. So compared to these guys, there is no inner negative charge. So all of these guys actually see the positive charge in the middle, right? But for this particular case, because the 2 negative charges are inside the outermost negative charges, they actually see the 2 plus charge. Now let's do a little bit more interesting case. So if you actually put one extra positive charge in the middle and then the one extra negative charge at the outer orbit, then what's going to happen is that each one of these outer orbit actually sees this whole thing having a 3 plus charge. Why do I say 3 plus charge? Because 5 minus 2, right? 5 positive charge and then 2 negative charge makes like a 3 plus. So if it's really too far away, this negative charge actually sees sort of like effectively a 3 plus charge in the middle. So each one of these guys actually attracted to this 3 plus charge, right? Compared to this one right here, each one of these 2 electrons actually sees a 2 positive charge in the middle, right? So which one of these outermost negative charge gets attracted? Is that this case or that case right here? And answer is literally obvious here, right? That 3 plus charge right here gets attracted more to the middle than this case right here. They only have a 2 plus in the middle, so they don't get attracted that much. That's the basic concept of the Z effective. Now let me just try to explain that one in the next several slides. In the quantum mechanics versions, so boron atoms have 5 protons in the center, right? So they actually have a 5 plus in the middle, and then electronic configuration, the ground state electronic configuration of the boron is 1s squared, 2s squared, 2p, right? The outermost electrons are one of these guys, any one of these guys, right? And what electrons that's orbiting in the middle is the 1s squared. I can't really tell you exactly where they are flying because that you cannot pinpoint the position of the electrons, but I know that these 2 electrons are close to the middle because the principal quantum number is 1. That means that it's smaller, right? So 1s squared means that you have 2 electrons orbiting or having the position close to the middle, right? Somewhere around here, right? those having the 2 electrons here. Now 5 positive and 2 electrons. So what the outer electron actually sees in the middle? 5 plus minus 2 electrons. So center charge is actually 3 plus for the boron case. Now let's go to the carbon. Carbon, the ground state electronic configuration is 1s squared, 2s squared, 2p2, because carbon have 6 protons, right? So the neutral carbon atom have 6 electrons. Now the core electron, just like the boron, it has 2 electrons, but carbon actually have 6 protons, right? So 6 protons, 2 electrons. So, and then each one of these 4 valence electrons, each one of those see effectively a 4 plus charge in the middle. So the valence electron see 4 plus charge at the center, right? Because there is 6 positive charge and then 2 electrons that's orbiting very close to the center, right? So carbon, the valence electrons of the carbon have a 4 plus charge attractions, whereas the boron actually feels the 3 plus attractions. So which one is smaller? Is going to be smaller. It's actually carbon, right? The carbon actually outermost electrons, those guys are attracted by the 4 plus charge, so it gets contracted. But for the boron atoms, because there is only 3 plus charge in the middle, it doesn't get that much attractions compared to the carbon. So the atomic size of the boron is slightly bigger than carbon. And that's the basic concept of the effective nuclear charge. So to actually put all those things in the word, the Z is the common letters for nuclear charge, the number of protons in the nucleus of an atom, and the Z effective, this is the effective nuclear charge, is defined as the magnitude of positive charge experienced by the electron, outermost electron in the atom. And then as the G effective increases, then the size of the atom decrease, and the Z effective increase from left to right across the periodic table. The charge, it changes very little down the column. So that the vertical way, it doesn't change that much, but if you go from left to right in the periodic table, it increases. So let me just try to say that. So Z effective actually increase this way. It really doesn't change that much, but in the vertical way. But these guys, the effective increase. And any one of these guys too. But each row, they don't change. This row and that row, there is not much of a difference for the Z effective. So where was I? And the shielding is a concept that actually explains the Z effective. The shielding occurs when an electron in many atoms is partially shielded by the positive charge of the nucleus by other electrons in atom. It's actually the core electrons. So the core electrons shield most and are constant across the period. What it means is that carbon atom have a 2 core electrons, right? Boron have a 2 electrons, nitrogen have a 2 electrons, oxygen have 2 electrons, the core electrons. The core electrons for B, C, N, O, F, and E, they all have the core electron of 1s square. The 2 electrons that's occupying the 1s orbital. 2s square to p of any kind, like 2 or 3 or 4, these guys are all valence electrons, right? So any one of this B, C, N, O, F, and E, they all have the 2 core electrons. But number of proton changes too, right? So the number of proton changes from 5 to 10, going from the B to N. So that the effective nuclear charge increase if you go from left to right. And finally, that when I say that Z effective, for example, oops, not that one. Z effective for this these things right here. For the lithium, it's a 1s square, 2s, right? And then the center charge is 3 plus, right? And then the core electron, number of core electron is 2, so 3 plus minus 2, right? So the outermost electrons, this 2s electrons occupying the 2s orbital, see there's a 1 plus charge in the middle, and then BE have a 1s square, 2s square, right? And number of proton is 4. So the but core electron is 2. So these 2 electrons, the valence electrons in the 2s orbital, actually sees a 2 plus charge in the middle. And then for the B atom, it's going to be 3, and then carbon, it's going to be 4, N is going to be 5, oxygen is going to be 6, fluorine is going to be 7, and neon is going to be 8. Right? In the very simplified approximations. Not really the case. It's sort of close, but it's not like that. So what's expected is like 3, 4, 5, 6, 7, and then Na is going to be 8, right? That's not really the case. It's actually that much less than that. And that, of course, it comes from the electron-electron repulsive interactions in the same outer orbit, or the valence electron repel each other too. So they actually have a little bit of different numbers, but yeah, it's the generic trend is increase in this way, right? Going from the left to right in the periodic table. So does the actual Z effective. It actually increases from left to right. So we don't really care too much about this actual number of the Z effective. This is probably good enough to actually explain the qualitatively what's happening in the size of the atoms, or what's happening to the reactivity and the ionization potential and the electron affinity and so on and so forth, which I'm going to explain later on. So, alright, this portion of the video is done.